Recently, I came across this very interesting article on Medium. Basically, it's about the thesis expressed in the title of this article that the best engineers rather think like investors than builders. And probably when you are designing new systems, you want to build something, of course, you want to build it in the best way. And what the best means, probably mostly in our case, is that we think we want it should be built in the most latest, most fully fledged, most scalable, robust technologies that are in the market. However, it's also good to look at those older approaches, probably currently deprecated for some reasons, but in many cases they are still sufficient, and with those approaches we can build the same things cheaper, faster, maybe with less risk involved. And anyway, if you are not going to use those technologies, like either way, after the investigation, it's good to learn their good and bad points and compare them with those all fancy cutting-edge technologies that would be your first choice, just to maybe stress the factual strengths of those fancy technologies that sometimes may be hyped and sometimes may really add some value to your project. So hello, I'm Krzysztof. My everyday activities revolves now around data engineering, for which I'm using Scala. However, I'm quite passionate about architecture of software systems, and I think data engineering is not that far from like architecture role, as we often spend our time designing the pipelines, data pipelines in performant way, and making them scalable and so on. And I'm working at SwissBorg. This is quite cool Swiss company that has a mobile app for trading cryptocurrencies. And maybe you know, maybe not, we are currently in middle of crypto winter. All the prices of crypto coins are low. So it is the best time to buy. So we can buy the cryptocurrencies with our app. However, disclaimer, this is not a financial advice, and you always make your investments at your own risk. Remember this. And what about you? How many of you has worked with any web application? Okay, most of you. That was kind of expected. And how many of you have worked with JVM, any JVM languages? Still, vast majority. So I'm going to talk about threading for web applications on JVM. That's why I asked. And this is the agenda for my talk today. I'm going to firstly make some context introduction about the context of the analysis that I'm going to describe later. Then I will give background for both approaches that I will be comparing, the thread per request approach and thread pool per operation. Then I'm going to execute comparison of those two approaches, specifically looking at two cases, and then finally I will provide some solid data to just illustrate the analysis that I shown before. So let's start with the context introduction. So this is a simple web application endpoint controller. And let's imagine we are developing a web application for buying cryptocurrencies. A typical request, for example, for buying cryptocurrency would consist of a sequence of operations. Like when user sends a request for buying cryptocurrencies, firstly we will read some data about this user, about its current assets that it has in our application. Then we probably will perform validation, confirm that particular user can buy this asset, he has enough fiat in his account, and there's also no ban posed on this user. Then we'll factually execute the exchange, probably by calling another service. After receiving a response, we will reevaluate the state of the app, basically the current balances of his account. We'll update the database and prepare response to the client. And this request is a kind of representative of the request that we have in web applications, because it consists of blocking and unblocking operations. And basically, typically, the blocking operations take more than 50% of the time of like typical query that is executed against a web application. And another characteristic of web applications is that we have unpredictable request volume. So for example, during night, there won't be probably much transactions happening in our cryptocurrency web application. However, if in the morning Elon Musk tweets about acquisition of Bitcoin, we may expect a huge load of buy requests, and we need to cope with those loads, like with those unexpected request volume. This is like the state of what we need to cope with in web application context. And one slide about thread mapping models. So in different languages, there are different approaches for mapping the representation of thread on application level towards the factual thread that runs on operating system level. So first approach is that we can have many logical language level threads mapped to a single physical operation level thread, like with which kernel works. And this is, for example, a case in Erlang language. And then we call those logical threads on application level green threads. The other approach is that we have exclusive one-to-one mapping between language level threads and operating level threads. And whenever we create a language level thread, operating level thread is also spawned. And the third approach that we have many-to-many mapping, which is dynamic. There is no like exclusive association between those two. Like a pool of threads on the application level are mapped to a pool of threads on operating system level, and language like takes care of this mapping. And the question to those who work with JVM is, what model is in Java, in JVM in general? I've heard two answers, the second and the last one. Like basically in Java, currently we have the second one, the middle one-to-one mapping. However, there's a big initiative happening in JVM world that is called Project Loom that is going to introduce the third model as an additional model that we can use in Java. But I'm not going to like analyze this one. I'm going to focus on the current one that we are having now. And what are consequences of this mapping is that threads are basically a heavy resource in JVM. They are relatively long to start because like the physical thread needs to be started at kernel level. Like relatively because like factually it's still less than 100 microseconds. And threads are quite big to store in memory. We need to assume that one thread takes 1 megabyte of memory. So yeah, if we have 1,000 threads, 1 giga of memory is taken. So we need to be cautious about thread. And also because there's this one-to-one mapping, the whole scheduling of thread is delegated out of the Java runtime to the operating system level, and JVM has no influence which thread will be scheduled next and for how much time. So that is about the introduction to the context of today's analysis. And let's look on the first approach, thread per request model. So this model comes from quite old Java EE, and Java EE was an initiative in Java space for standardizing various functionalities that we may need from our application runtime. So for example, dependency injection, persistence layer, messaging, validation, and so on. So there was specification of interface. You wrote your application according to your interface, and then you had the freedom to choose any of the implementations of those interfaces that were in the market, and those implementations were called application servers. And for example, you could choose JBoss, Glassfish, Wi-Fi, and so on. And yeah, those specifications were under a common package called drawbacks. And one of those specifications was servlet API that basically is one of the few that survived test of time and it's still being successfully used. And this API is for creating web applications. So it creates a framework of dealing with web things in particular way. And those web things are, for example, authentication, sessions, cookies, transactions, and so on. And it also introduces a certain way of dealing with threads regarding request processing, which is this thread per request model. And yeah, one of the currently used implementations of the server API is a Tomcat. And this Tomcat will be a tool that I'm going to reference to on the next slide. So how does it work? So this black rectangle is our application. Inside our application, we have worker thread pool. We have also acceptor thread that will accept upcoming request. And when the connection with request comes, to be precise, it's first handled on the operation system level, because HTTP request is factually on lower level a TCP/IP connection, and this connection is negotiated first on the operating system level, and only when the connection is negotiated, then the connection is made available for the acceptor thread to take it from the system level queue and start reading data from it. So when the acceptor thread takes the connection from the operating system, it starts reading the data. When the data comes, the request is ready to be processed. Then this request is dispatched to the worker thread pool. And from this moment, one request is exclusively associated with this request. And this thread will process the whole handling of the request all the way. And this approach has specific characteristic, because when we associate one thread with the request, we can utilize thread local variables, which may be seen as little dirty and factually is. However, in return, it's quite useful, because a framework knows that in thread locals, it will find the context of this request. So the framework can provide a lot of useful functionalities for web handling out of the box. For example, authorization guards on the methods, transaction management, some tracing added to logs, and so on. So it utilizes thread locals and basically removes a lot of boilerplate for our code that we write. And basically handling requests works in this way: that next connection is taken, a request is collected, dispatched, and so on. And it goes up to the moment when we basically allocate all the threads that we had in the pool. And basically, this worker pool is limited, and there is in Tomcat there is a parameter called max threads. Then its default value is 200. That limits the size of the thread pool. So in typical Tomcat application, you can have 200 threads processing concurrently requests. So the concurrency level in this case is that at the same time, we can process 200 requests, and when the next request comes, it's not processed until one of the threads is freed. Yes, it waits. And what about then blocking operations? As we showed previously, part of processing of the request is part of processing is basically executing blocking requests. So if one thread executes this handling, then this request will block. And well, question: isn't it bad that the main thread executing handling of requests blocks? And shouldn't we delegate this blocking operation to some other asynchronous processing? And what if what about CPU time utilization? Like when we block thread, then we do not compute anything. What about CPU time? So first of all, it's good intuition to think about blocking operations as the ones to be delegated asynchronously to some other place. However, this makes sense if those calls are independent. So if we have 3 blocking calls, each lasts 2 seconds. In total, we wait 6 seconds if they are called synchronously. But if we put them asynchronously, we can parallelize the waiting time, and then we wait 2 seconds in total. But this is only possible when those calls are independent, right? In case of web application, often it's the case that to be able to trigger the next call, we need return value from the previous one. So we can't go for this parallelization. And in this way, there's no way to shorten this time of executing those blocking calls. So in this way, we won't get any advantage of going like for asynchronous computation. And regarding the CPU time, the thing is following. We have a worker thread pool that can spawn to up to like 200 threads. So we have much more threads than cores on the machine, which means it's totally fine if even the majority of the thread is blocked, because there will be still some cores that could process and utilize CPU time. So when one thread processing request executes reads from database, another thread can like be awakened and continue its processing. So we can expect that there will be always some other like work to do that will like burn our cores on CPU. And the question to you, how many cores do you give normally to your web application instance? Well, I would guess that typically like these are 2 cores, 4 cores, 8 cores at maximum, because it's better to create multiple instances of web application with lower number of cores than create one big with like, I don't know, 28 cores or something like this. So this is regarding the thread per request model. And let's move on to the thread pool per operation approach. So to start with, this approach is not coming from any particular framework. This is just plain way of executing some operations in a synchronous way. So instead of having a procedural script of things to execute, we made a big chain of asynchronous calls. And typically in functional languages, we utilize some monad for this reason. In this case, I'm using Future because I'm going to show some examples in Akka Http, and Akka Http relies on the Future monad. However, it can be any other one that allows for asynchronous execution. And the important thing is following that for each operation in this chain, we can specify a different thread pool. So conceptually, each of those operations can be executed in different threads. So here we cannot use the same approach from Java EE to put anything in thread locals because threads are unrelated to requests. And the best design is to separate the blocking calls out of non-blocking calls and have separate operations for both of them. And then to dispatch blocking calls to one thread pool dedicated for blocking calls and non-blocking for another thread pool dedicated for non-blocking calls. And the sizes of both should be following that the blocking one should be big. It cannot be unbound because we need to limit the memory that we are consuming, but it should be quite big. And non-blocking operation thread pool should be sized according to the number of cores that we have on the machine. And how it will look like when compared to the previous approach is that regarding the accepting connections and collecting requests, it looks almost identical. However, we do not have one worker thread pool. We have 2 thread pools, one for non-blocking and one for blocking operations. And when the request comes in, it's basically being executed as short like operations in different thread pools, as it's shown now in the slide. And one disclaimer, as I said before, this is not like tied with particular framework. This approach can also be implemented in servlet API, in servlet container. However, it's not doing that often in the servlet container environment. It's mostly done in like more functional programming frameworks like Akka Http. Okay, and let's now compare those two. So first of all, a closer look into how thread pool works. So thread pool is a construct, as shown in the diagram, that has a queue of the tasks. Those tasks are runnables. So those green threads, those threads represented as green squares can take tasks from the queue and execute. And basically the code that is run inside the thread is following that this is the loop, infinite loop, that consists of two operations. First one is pop next tasks from the queue and then execute it and then repeat. And as I said, those tasks on the queue are runnables. And in case of thread per request approach, one runnable is the whole handling of the request. And in case of thread pool per operation, one runnable will be a single operation. And one slide about states of the threads. So again, a thread pool here is a big rectangle. And inside this rectangle, like inside thread pool, threads can be in different states. When the thread pool is idling, all of its threads is in waiting state for tasks. When the task comes, it starts being executed. It's moved to the ready state where it waits for CPU time to be given. When it's given CPU time, it's factually executing. When it executes blocking call, it's moved to the block state, waiting for the blocking operation to finish. And when there is unblocking, it gets back to ready state and it's being ready for further execution. So let's then analyze typical scenario for the thread per request approach. In this approach, we'll have some threads in the waiting state, some threads currently executing blocking operations, so being blocked, and some threads actually executing non-blocking code, among which the CPU time will be distributed. So the highlighted ones are ones currently executing code, but then operating system scheduler kicks them out of the processor, gives time to another CPU time to another threads, and it goes on. And of course, tasks can move between those states according to the operations that are executing. So first case that we'll analyze, peak of blocking operations. So what will happen if at some time we have a huge load in our application, and it will happen that all the the current processing in all threads will become blocked. So all our thread pool will be basically in the block state. So the number of threads here is the number of the limits that we have for our thread pool. Then we are not using CPU at all, because all things are in block state, so nothing is to be ready to be scheduled on CPU core. And so yeah, we are wasting CPU. And if the next request comes, because all the threads are taken, it waits for available thread. So there are some other operations to execute. We have CPU not working, like CPU idling, and we still are not processing further requests. And yeah, obvious idea would be, yeah, let's increase the pool, but we cannot increase it to infinity, because we need to mind the memory limits that we have on our machine. And then another approach, another case that we want to look at is a peak of long-running non-blocking requests. So the contrary situation. So we have a lot of requests, but most of them are basically non-blocking and awaiting CPU time. So we may have something in like some threads in waiting state, we may have some threads in block state, but what we look at is that we have most of the threads or many threads in ready or running state, and then like long running, meaning that those operations will run for more than one time slice of the operating system scheduler. That means that they would need to be preempted from the CPU core. So as we see now, some threads are executing, then CPU scheduler kicks in and switches context and switches context again, and so on and so on. In this case, there will be a lot of context switching between those threads, and we will like execute suboptimally, because some time will be wasted for this context switching. Like we have a lot of those threads in running state, and there would be need a lot of context switching involved here during the runtime of application. So let's look now how the things work with the second approach, thread pool per operation. So typical scenario is following, that we have two thread pools, one for blocking operations and one for non-blocking. The one for blocking is big, so that we can wait in parallel for as many blocking operations as we can. And we have non-blocking sized equally to the number of cores, so that when we will execute a non-blocking operation, we will reduce the context switching, because there won't be more cores more threads than cores on the machine. So when there is some blocking operations being dispatched to this thread pool, like thread allocates the task, goes for a very short time to the running state just to execute the call, the blocking call, that it lands in blocked state. It waits for the blocking operations to finish, and then it's for a short time return for the running state, and then basically the task is completed. In case of non-blocking thread pool, situation is similar, that the task is taken, it goes to ready state, then it gets CPU time, it executes this non-blocking operation, task is finished, and then either it takes next task or gets back to the waiting for task state. And the important thing is that here we won't enter block state at any time. If we design properly the chain of the operations, here we won't submit any blocking calls, so this state won't be used in this case. So in case of peak of blocking operations that we analyzed before, we'll have following situation. All cores for the blocking pools are taken, and then if next task comes, we have two options. If this task will involve some blocking operations, those blocking operations will need to wait. There won't be thread for them to execute those blocking operations. But if there's some request that consists only from non-blocking parts, that it can be processed without any problems in the other thread pool. So this is the situation when we were blocking many things, but we can still utilize CPU if the new request requires only non-blocking operations. So it goes to ready running state, and it will process the request. And what in case of a huge load of non-blocking operations? In this case, we can have whatever is possible in the blocking pool, but however, in non-blocking pool, we'll have only that number of threads running that we have the cores. So here, the context switching will be limited, because at most, here we have, for example, 4 threads here, meaning that we have 4 cores available, and all other running tasks are basically awaiting their slot in the thread. So when one task is finished, slot is made for another task, it's taken, and it's being processed, and context switching is limited. So a demo that I executed, basically a benchmark. So I created 2 versions of web app, and those web apps had 2 endpoints, one executing a blocking operation, and for benchmark purposes, this blocking operations was taking 3 seconds, and another one executing non-blocking operation very fast, around 30 milliseconds of execution time. And the load I put was following: 200 calls to the endpoint that blocked, and 50 calls, and then after some time, 50 calls to the non-blocking endpoint. And for this benchmarking, I use Gatling. Probably you know this tool, very nice tool for testing the load capabilities of our application. And this is the code that I used in Gatling for this load test. So, and quickly, a short glimpse on the code. This is the code that I wrote in Spring Book on Tomcat, very basic one, and the adequate code that I wrote in Akka Http. Basically, syntax different, but the logic the same. And here, what I want to stress is that I use 2 different thread pools, one blocking operations, thread pools in Scala are called are called execution context. This is why there's EC suffix. So blocking operations execution context and non-blocking operations execution context. And the results are following. So in case of Spring on Tomcat, yeah, the timeline is following. 200 calls for blocking operations. Each of them lasts 3 seconds. So the whole execution lasted here 3 seconds. And we see on the Gatling report that the minimum time of the execution of the call was 3 seconds, and the maximum 3,000 milliseconds, 3,200 milliseconds, the maximum. So as expected. But then, if after 2 seconds there were like 50 calls to non-blocking operations called, basically this was a very short operation that should finish immediately. It needed to wait like this 1 second to finish of the previous calls, and only then it was executed and finished. So we see in the diagram that those 50 calls took more than 1 second. And in case of Akka HTTP, the performing time of those 200 calls was similar in the previous time, but those additional 50 calls to non-blocking operation finished immediately because there was still this non-blocking pool was available for processing. And we see that the values in the Gatling report show accordingly. The maximum time of handling those calls was 70 milliseconds. So to sum up, so basically, characteristic of those two. In the first approach, thread per request, we have this possibility to use thread locals that in turn gives us bigger support from the framework. In thread pool, thread pool per operation, we do not have this characteristic. However, it should be seen as more cleaner approach, but as well there's more responsibility on developer side. And in those two cases, in peak of blocking calls, the first approach causes that when we have peak of blocking calls, no other request can be processed. In case of thread pool per operation, we can still process some non-blocking requests as we show in the demo. And in case of peak of non-blocking calls, the first approach would suffer from a lot of context switching, which will be suboptimal for request processing. And the other approach, the thread pool per operation, will be freed from this context switching overhead. And to sum up, the first approach is generally a good one, but with potential issues on edge cases. The other one is more difficult to implement, but it doesn't suffer from those problems, so it's better suited for biased load that may happen in our application. So that's it from my side, and yeah, maybe now time for questions.
Yep, thank you, Krzysztof. That was I really liked the opening quote. So we're going to go with questions of Ermi, and it looks like we do have some. So the writing is a bit small. I have to stand here to read it. So what is the usual best practice for deciding the size of a thread pool for blocking operations, just to decide how much RAM I afford to give to the blocked threads?
Yeah, so first of all, you need to analyze what capabilities you have in your environment, how much RAM do you have. And then you need to analyze basically execution time, to somehow measure the metrics of your system. So different systems have different proportions of blocking to non-blocking operations. And the best way is probably to start with some default value like those 200, and then analyze with some JVM monitoring tools how the things look like. If we happen that, our blocking operations thread pool is always reaching its limit, and then we have still some memory left on our machine, because the consumption of the heap is not that big, then probably we can increase it. So I would start with defaults and then monitor and then decide if we can afford increasing the limits and if it's needed at all. So that would be my answer.
that was the only question off of Ermi. Do we have any more in person? Great.
Okay, a great talk. And my question is, I have a concern for the tests you perform.
Yes.
Because for the Spring application, you use 200 threads, right? And for the Akka, you use 200 threads for blocking and 16 for non-blocking. So it wouldn't be better to have total number of threads equal to test the capabilities?
Yeah, very good point. So I did it like to have like very clean results here, because what would happen if we would decrease the size of the blocking thread pool? The maximum value here would be higher, because out of those 200 calls, okay, so we have 16 threads for non-blocking thread pool, so we would need to have here 184, right? So 184 calls would finish here, right? And those missing 16 will need to wait another 3 seconds, right? So yes, in this case, we will have like the greater time for completing of blocking calls that came to our system. However, this won't affect quick completion of those 51s here. Yeah. So that would be the only difference if I did this.
I see. So there is basically, but this is also a bit of trade-off that we need to do.
Yes.
To take into consideration.
Yes.
And do you run some tests, for example, what is the best ratio for blocking to non-blocking threads?
Okay. So this is not about the ratio, because for non-blocking thread pool, you need to have it fixed to the number of cores that you have on your system, and then the size of the blocking thread pool depends on the memory that you have. This is the similar situation that we were talking about in previous question.
Yeah, I see. Thank you.
Okay. So another question.
Yeah, hello. So firstly, I would like to ask, how many trades per second does the exchange handle?
How many again?
Trades per second. Do you have some API for traders with bots? Do you provide it, or does your exchange provide it only to clients?
So you're asking about our product?
Yeah.
So basically, as I said, I'm working as data engineer in my company, so I'm not exposed to this type. But well, so yeah, I can't provide the details how many trades per second we have. Or maybe I know it. No, I can't. I just don't want to guess.
Yeah, okay, that's fine. But my actual question was, you have measured just a single layer with Spring and with Akka Http. You haven't built a pipeline that you have described before in the slides. So I expect that if in Spring you would do something similar, if you would try non-blocking calls in different threads, the results would be almost the same. But I think that it needs to be measured in more complex pipelines of data.
So for sure, this benchmark was a kind of artificial one, just to show the clear distinction. However, if you analyze the typical flow that you have blocking and non-blocking ones, minding that blocking calls takes much longer than the non-blocking operations typically, right? Because like blocking over the networks is much more than even computing some validation and so on. Then you will have majority of things waiting for in this non-blocking state. And then, yeah, if you have, okay, 200 requests won't be enough, but you have 300 requests and 200 like blocked. So then you can't process any more. So it would be similar. Here is like artificial example just to show the real difference, but it's basically, it can be scaled to the example then we have like mixture of them.
Okay, so we still have time for a few more questions. It's impossible to get to.
Yeah, microphone delivery.
Yeah.
It's not that easy in this room.
Hi, thank you for the talk, it was great. I have also, again, a few questions and concerns about the demo. We have shown the worst case scenario for threads per request, But as some other people pointed out, if we assume that the non-blocking time is really small, does it really matter? And of course, every millisecond matters, but why is nobody, why are there systems that still use this thread per request model if this one is obviously better? Yeah, because it's generally a good approach, right? So as I said here, so basically, I was comparing this old approach with the newer one from functional programming, just to say that there are some cases that functional programming approach with those like chain of asynchronous requests does better than the previous one, but the previous one is really good. Because normally, yeah, we have this like mixture of blocking, non-blocking, so there will be still some threads in non-blocking state that can utilize CPU time, and yeah, application as a whole is performant. But yeah, here it was the comparison, the real strength, like those features, why those thread pool per operation is better, are those edge cases. However, the previous one is, yeah, still good. Mm-hmm. Yeah, you have another question. No, I think that's it. Yeah, is there any actual limitation that the Tomcat server just chooses this model, or they just don't bother to update it? It's not a limitation, it's a trade-off for gains that they're getting. Like as I said, going for thread per request framework allows for using thread locals. Yeah, someone would say using thread local is dirty because it's more difficult for unit testing and for some other things maybe. However, yeah, it gives a lot of intern, like that. Yeah, your framework can give much more support in this way. Yeah. So I think that was the decision, just minding the gains that we get from this. Thank you.
Okay, so there was one more question, and we still have time for it. Could you raise your hand again? Who? Thanks.
Hey, thanks a lot for your talk. It was really interesting perspective. And I am not going to ask a question about the demo for a change.
Okay.
I wanted to ask about your perspective in case of using asynchronous execution, for example, like it is in Kotlin. What change could be there in this thread pool approach, and what do you think would be what do you think would be the biggest concerns about using it?
The biggest concern, like from my perspective, is that, for example, like I mentioned about this quickly on the slide, but let's get back to the particular code, and maybe I will. It would be better to show it here. So many clicking to get back, but we are close. Okay, here. So the thing is following: when you have this chain of calls, any context information needs to be wrapped with this X parameter, right? So that like we are reading here the data. You have some value, you're passing this value here, but you need to wrap it with the contextual information regarding the transaction ID, regarding, I don't know, the session and so on. So going for this approach in case of web applications, like adds you additional concern and additional burden of managing additional syntax wrapper and so on. Regarding the, maybe you, I may assume, maybe you ask about the performance reasons. I don't know. Probably it's just, well, performance reasons are better because it's like better suited for those edge cases. So yeah. So I would see only concerns as regards the additional amount of code that you need to write to handle the particular context of web application.
Okay, so we're done with time. Thank you, Krzysztof.
Thank you very much.
Another round of applause.